Okay, here's the solution to homework set number 1 for ECE 321 for fall 2021. The first problem is design a couple of filters. The first one has a gain of +3, the second has a gain of -3. For a gain of +3, there's a couple solutions. Here's one of them. I can build a non-inverting amplifier. Non-inverting amplifier, again, V plus equals V minus for op amps. We have negative feedback. This is a voltage divider. X is 1/3 of Y, so Y is 3 times X, or the equation for this one is 1 plus the ratio. 1 plus 2K over 1K. For gain of -3, I can use this configuration. That's an inverting op amp. Here the gain is minus R1 over R2, minus 3K over 1K. And the resistor values are kind of arbitrary. As long as it's a 3-to-1 ratio in this case, 2-to-1 ratio in this case, it works. Up to a couple limits. The max current for the op amps we're using is about 50 milliamps, so these have to be at least 100 ohms. Plus the input impedance is like 4 giga-ohms, so keep the resistors bigger than 100 ohms, less than 10 mega-ohms, and they're pretty close to ideal. Part C is implement the function 12 minus 4x. So here the trick, it's a 4K. Those oopses. Here the gain of the op amp is your R1 over R2 times your A minus B. And here's A, the plus input. Here's B, the minus input. In this case, matching terms, I want the gain to be 4, so pick this to be 4-to-1 ratio. I want 3 to be A, so A is 3 volts, and X is B. Again, one way to do it. There's other ways. A mixer. Come up with a circuit to implement 6A plus B plus 3C. One way to do that is create a dummy variable X. X is going to be this over 10 is the weighted average. And kind of where I got the number 10 is 6 plus 1 plus 3 is 10. If everybody is 1 volt, X is 1 volt, kind of by symmetry, so they have to add up. Once I have X, if I multiply by 10, I'll clear the denominator. So build an amplifier with a gain of 10 times X, and I got it. So again, this is 1 plus the ratio. A 9-to-1 ratio gives you a gain of 10. And to give a weighted average, I just use the trick. Pick a resistor. I chose 10K. Make the weighting of AA 6, so this is 10K over 6. The weighting on B is 1, 10K over 1. Weighting on C is 3, 10K over 3. This is the weighted average times 10 gives you 6A plus B plus 3C. One way to do it is you could use inverting op amps. Here the gain is R minus R1 over R2. So this has a gain of minus 6 times A, minus 1 times B, minus 3 times C. That gives you minus Y. Times minus 1 gives you plus Y. Either one works. This takes 2 op amps. This takes 1 op amp. On paper, either one's fine. Problem 3. Design a circuit so that Y equals X, subject to the constraint that X is less than 10 milliamps and Y can be up to 200 milliamps. So there the trick is use a power transistor. In Circuit Lab I used a TIP 31 for NPN, TIP 32 for PNP. Just something capable of 200 milliamps. Here what the circuit does is when the voltage is positive, say 1 volt, V plus equals V minus, this is 1 volt. When the voltage is positive, I have current flow going down. This is a 0.7 volt drop, so this will be 1.7 volts. And the NPN is turned on, PNP is turned off. When I'm at negative 1 volt, let's do that in red. Thinking, trying to get my draw to come up in red. Here we go. When I'm at minus 1 volt, V plus equals V minus. This is also minus 1 volt. And current's actually going up now. Okay, current can't go through the NPN backwards, but it can go through the PNP. So now the PNP turns on. And this will be 1 volt minus 0.7 minus 1.7 volts. So this is your push-pull. Positive voltage, the NPN turns on, that's push. Negative voltage, the PNP turns on, that's pull. If I simulate that in Circuit Lab, look at the voltage at V0, V1, and V2. Here's what you get. V1, V0 equals V2, input equals output, that's Y equals X. The voltage at the base has this jump. This is over here is the push part. When the NPN turns on, the voltage at the base goes up by 0.7 volts. Over here, when it's negative, I have the pull part. When the voltage is negative, the PNP transistor turns on, and it comes down another 0.7 volts. In hardware, if you build, the last part is to build a push-pull amplifier. Actually, there's just a push amplifier on your breadboard. So you can amplify songs, mix the songs together. We'll use this again in homework 3 when we want to build a filter. Right now, I just want to take the headphones from your computer or from your cell phone, amplify it to drive an 8-ohm speaker. Now, a problem we have is we only have 5 volts and ground on our breadboards, so I need a 2.5 volt reference. I want to take the audio signals and center them on 2.5 volts. The reason being is I only have 5 volts and ground. So if I center the signal at 0, I'll clip. I can't go negative. Centering at 2.5 volts lets the sine wave go plus minus. So this guy right here, 2.5 volt offset. This is an amplifier. Takes your cell phone and multiplies it by 4, a 3-to-1 ratio. Well, gain is 1 plus the ratio, gives you a gain of 4. And then here's the push-pull amplifier. Whatever this voltage is the voltage at the speaker. What the transistor does, this has a gain of 200. 1 milliamp at the base produces 200 milliamps, actually 201 milliamps at the emitter. It's 200 milliamps at the collector, 1 milliamp here. Add them together, you get 1 plus beta, 201 milliamps. So the op amp only has to supply 0.5% of the current to the speaker. To analyze it, suppose the input is 2 volts, so below my 2.5 volt offset. In that case, V plus equals V minus. This is 2.5 volts, so I have 0.5 milliamp going up. That current has to go through here. That gives you 1.5 volts. 2 minus 1.5 gives you 0.5 volts. V plus equals V minus. V3 is 0.5 volts. And 0.5 cross 8 ohms is 62 milliamps. If I change the input voltage to 2.5 volts, and V plus equals V minus, this is 2.5, that's 2.5. No voltage drop means no current. For continuity, there's also no current, so this is also 2.5, 2.5. 2.5 volts in gives you 2.5 volts out. And 3 volts in, 0.5 volt above your 2.5 volt offset, gets amplified by 4. Output equals input. So 0.5 volt above gives you 2 volts above, 4 times 0.5 volt. And now I have 562 milliamps. So this is a circuit which will amplify the voltage at the input by 4, amplify the current so I can drive an 8 ohm speaker. That's the analysis part. In Circuit Lab, I can check my answer. If I take my input, do a 0.5 volt peak-to-peak sine wave, offset by 2.5 volts, I don't have to do it this way. I could actually just double-click on this, make the DC offset 2.5 volts, the AC amplitude 0.5 volts. The 7K is in there for the mystery reason. It doesn't do anything. Ignore it. Here's my gain of 4 amplifier. Here's my push amplifier. If I simulate it, what you'll see is the input goes 2.5 volts plus minus 0.5 volt. There's your plus, minus 0.5 volt. The output's also at 2.5 volts, amplified by 4. Goes plus 2 to minus 2 volts from my center, from my circuit ground. That's in simulation. And hardware, if you build the circuit, again, kind of like this, here's the headphone. This is the power supply. Provides plus 5 volts, ground. This one I removed the jumper, so this guy's floating in ground. This actually goes to the first op amp. Here's my 2.5 volt offset. So this is circuit ground, 2.5 volts. The second op amp is my times for amplifier. So here's my voltage divider going to the output. That then goes to my push-pull amplifier. Here's your V plus, V minus resistor. If I look at the voltage at the speaker, here's what it looks like. If I have a 44 millivolt sine wave coming in, the output is 4 times as big, as I expect, and it's a sine wave. So it's not distorting it. Sine wave in gives you sine wave out. That's analog. The fun part is apply a song. Songs are a little bit harder to measure and analyze because that's kind of what it looks like. It's kind of a random signal. A lot more fun to listen to. This is Hot and Cold by Elmo and Katy Perry from Sesame Street. That's what it looks like. More fun to listen to. If you want to hear what that sounds like, that is posted under the Homework 1 demo. So that's homework number 1 for ECE 321 Analog Electronics.